Okay, let's break down graphing these two trig functions, sine and cosine, the two basic ones. They look very similar in nature as well. I included the table that I often reference, and I included a quick sketch of the 4 points on the axes of the unit circle. And I didn't write in the coordinates for quadrant 1, but we're going to make that correlation here in just a second. I think the most difficult concept to grasp when we graph these is that we're switching from the unit circle, in which it's just a collection of points that have exact values on this circle with radius 1, right? This is not a graph necessarily of anything trig related. It's just a collection of all of these points that have exact values for really that function, right? X squared plus y squared equals 1 is the equation of a circle that has a radius 1. So the graph of sine and cosine they're not going to end up looking like a circle like this. We're taking the information given on that unit circle, or in this chart I drew, and graphing that function. So the question is to graph f of x equals sine x, or we could just say y equals sine x, right? And therefore, these values that I put in this chart, those are the y values, right? These are y, where the top set of values is x. I'll go ahead and change this highlighter to a yellow, let's say. So if we were to think of x values ranging from 0 to pi over 2 to begin with, and we are plotting the respective y values that we have from all of those special angles in the first quadrant. Hope that makes sense. If not, here, let's start by looking at what I'm talking about. And you notice I drew this quite different than a standard, like, I don't know, a lot of people stick with like a -5 to 5 graph when they first start graphing a function, right? Well, we are in radians. That's another important thing to realize is I drew, or in my chart up here, I didn't use degrees, I did radians. It's far more common to look at, especially moving forward, almost everything in radians. It simplifies nice and it just works better than degrees. Okay, so as we move left to right, if I were to think of, we'll just call this pi over 2 right here, I'm counting by pi over 2, right? So therefore, this is about, that's a half a pi, this is about pi, we have negative pi over 2, and so forth. And in fact, for the first graph, oh, I didn't want to erase the whole thing. That's all right, I could draw that. I actually kind of want to look at all the way to 2 pi, and we'll see why in just a second. So remember these angles, we have a 0 degree angle, we have pi over 2, we have pi, we have 3 pi over 2, which is 270 down here, and then it goes to 2 pi and keeps going, right? So 3 pi over 2 and 2 pi. This is not our standard count, 1, 2, 3, 4, and so forth. All right, those are x values. That is our theta. So we could either say this is the x-axis, or we could even just say it's theta axis. It really doesn't matter. Graphing calculators really prefer x and y. All right, moving from left to right, our first coordinate, notice, is x is 0, y is 0, right? So we graph 0, 0 there. Our next coordinate is x is pi over 6, y is 1/2. Now really quick, I'm going to squeeze this in. The largest value we will get for sine is 1. Okay, and we'll explain why here in a second. The smallest value for sine is -1, and therefore the range is from -1 to 1, but we'll explain that in just a second. So let's move left to right. So pi over 6 Well, if this is half a pi, it's somewhere like right here, right? Is pi over 6. We get 1/2, something like that. Pi over 4 is exactly in the middle here, pi over 4. And my pi over 6 might be off a little, that's okay. Because this is like 3 pi over 6 here, right? 1/2 is 3 over 6. So if I were to cut it into thirds, I mean, it's close enough. Okay, pi over 4 is square root of 2 over 2. I don't know exactly what that is, but I know it's less than 1, and I know it's greater than 1/2, so somewhere right there. Pi over 3 is somewhere like right here, and that is square root of 3 over 2. It's getting close to 1, and then pi over 2, we finally hit 1. So what happens as we move beyond pi over 2? Well, that's where I wanted to refer to this unit circle. Sine corresponds to the y value. So as we move from the angle 0 to pi, right, our angle is increasing. Our angle is increasing. The y value increased from 0 to 1, but now as we go to pi, our y value is dropping from 1 back down to 0. So it's going from 1, right, all the way down to 0 here. So what are these other values? Well, remember that they're mirror images, like on the unit circle. This point corresponds to that point for the y, and here and here, and here and here, right? So therefore, these values I have here begin to go back down. Now again, referring to this unit circle, remember all students take calculus as the acronym. Sine is positive, quadrant 2, but once we move from the pi to 3 pi over 2, sine is now negative, and sine remains negative all the way to 2 pi where it hits 0 again. Once I remember, here's a quick shortcut of graphing y equals sine. Once I remember where it starts at 0, 0. Then I know at pi over 2 it hits 1. I really just need these 5 points here. At 3 pi over 2 it's -1, right? Because sine is y, corresponds to y in the unit circle. And at 2 pi it goes back to 0. And then it will repeat. Because remember, coterminal angles are the same. They have the same initial and same terminal side. They just may be larger than 360 degrees or larger than 2 pi, right? This is going to be cyclic, or it's a periodic function, which means it has periods of repetition. And it would do the same if I were to go back negative as well. Negative pi over 2 should hit here. So therefore, back here at negative pi. And then it continues to repeat this way as well. So one thing, or a couple things to draw off of this as well, is notice the domain for sine is all real numbers. X could be anything, right? We could do the sine of any angle. Cosine, however, only ranges from 1 to -1. It never gets outside of those values. It does include -1 and 1, so we use brackets, but it will never surpass 1 or 1 until we start doing things of this function, right? Think of that as our parent function. Think of that as our parent function. Remember, y equals x squared. Let's go and switch colors really quick. Y equals x squared is a basic graph like that. It's the parent function, but once I start, say y equals x squared plus 1, I move it up 1, right? Same thing with sine. Once I do anything to this function, it could adjust, but basic sine, that's true of domain and range. All right, that was a lot of explaining. Watch how quick we can do cosine, though, once we get where all this stuff is coming from. So let's graph y equals cosine x. Okay, I'm going to center this time. Okay, there's our x, there's our y, or, x is theta, whatever. I know cosine also only goes from -1 to 1 on the y-axis, its range, right? Because cosine is all of these x values over here, and the x values only range from -1 to +1 on the unit circle. So its range is only -1 to 1. But the angle, just like sine, can be anything. So already I know that the domain is -infinity to infinity, and the range is -1 to 1, just like sine was. Okay. So let's graph this. Whoops. Cosine. Cosine of 0 is 1. It starts at 1. As I move to the right, okay, I always want these four 90-degree angles, right? The 4 pi over 2. So as I move to the right, I'd hit pi over 2, and then pi. I'm counted by half. 1/2, 1, 1.5, 2. And we could keep going. 2.5, 3, and so forth. -1/2, -1, -1.5, -2, -2.5, and so forth. So x, it starts at 1, and then at pi over 2 it hits 0. At pi, x is -1. At 2 pi, 3 pi over 2, x is 0. And at 2 pi, it's back at 1. And now we started it all over because 2 pi is coterminal with 0. And same thing going backwards. If I went back, -pi over 2 is right here, right? -pi over 2. So we get 0. And then we'd get -1 and 0 and 1. Once you know the starting spot of sine and cosine, these are really easy to graph. Okay, they will always be cyclic. And until we start messing around with the function itself, those are the values we need. Now I stopped there, but we could have continued forward. Okay. When graphing these, you usually want to show at least one full period, one full rotation. In my opinion, it would be best showed just slightly more. So, if my viewing window on a calculator included something like that way I could kind of see the full rotation and a bit more, that's pretty good. Two full rotations, maybe even better.